So today I will speak about contact hyperbolic manifolds. Contact hyperbolic complex manifolds. So you probably heard a talk with a very similar title by Filippo Bracci when he was here in Ljubljana for the anniversary of the seminar. And perhaps you also heard me talk about this at a conference in Italy last summer. But if not, I'll just start from the beginning. So we have these three words, and I'm just going to explain each one by one. So I'm going to start with the last one, manifolds. Perfect. We all know what's a manifold, so we're done. Already a third of the talk is true. So let's go with contact, which maybe needs a few more words. So I'm going to talk about, as I said, complex manifolds. Contact geometry is in fact something that arises in the real geometry, but we'll only focus on the complex case and maybe mention some real things as well. So we take a complex manifold of odd dimension, and we take a holomorphic subbundle of the tangent bundle of rank 2n. So something that locally can be expressed as the kernel of a 1-form. And we require this form to have some extra property such that alpha wedge the alpha to the n is nowhere zero. So this doesn't look like this really is nowhere zero. So what is this form? So it's a 1 form, there's a 2 form to the n, this means the wedge product is a 2n plus 1 form, is a top form, on the top dimension, and we're asking that this is nowhere zero, so this is some kind of non-degeneracy condition, which then kind of represents this contact manifold. And we call such V is a contact distribution, or maybe the contact distribution. The contact distribution on the contact manifold. Yeah, so we call M equipped with V. In fact, the pair M and V is what we call the contact manifold, and such a V we call the contact distribution. And maybe just to get an idea of what this is, let's look at this local picture. So there is a called the blue theorem, which also holds again for real in the real setting. So we start with a contact manifold together with this contact distribution. We take a point in the manifold, then locally, so there exists a U neighborhood of P and coordinates, holomorphic coordinates. Z1, W1, do it with Zn, Wn, so these are 2n, and then we have the last one, which we call Y, such that V restricted to U is the kernel of a very specific 1 form, which is dy minus the sum from j equal 1 to n of zj dwj. So what this theorem is saying is that since every time you have a holomorphic subbundle of rank 2n, this is the kernel of a 1 form, and asking this extra condition kind of forces this form up to a change of coordinates to be this one, at least locally. Okay. So this is the picture you should have in mind. And as an observation, this means that there are no local variants. There are no local variants. Yeah, if locally everything looks like this, then well, there's not much we can say. Another observation that if you take any two contact manifolds and you want to study whether they're isomorphic in some sense or not, you're not going to find any obstruction at the local level. So any neighborhood of a point in a contact manifold is a contactomorphic, whatever that is going to mean, to any other neighborhood in any other contact manifold. And also, if we take this distribution, so of course I am saying that M is holomorphic subbundle, but you can also think of the space of section of this, and these are often interchanged. So if you take the distribution, so really vector fields with values in V, you can put them to oneself, you're gonna end up with any possible vector field. Yeah, so you can leave this distribution if you take brackets. So V is not Frobenius integral. Frobenius integral. And this condition here is, if you work it out, is precisely what ensures that V is not Frobenius integrable. And in fact, the fact that it is nowhere zero, not just that it's not the zero form, but it's nowhere zero, really tells you that at every point, you're not Frobenius integrable in some sense. So you can really not find, let's say we're in a manifold dimension 3, you cannot find any two-dimensional object which is tangent to this two-dimensional distribution. Okay. In general, you can find objects of a most dimension n, which are tangent to this 2n dimensional distribution. So let's make this local example global, just to have, again, something in mind. This is our very simple C3 with this z. Actually, maybe that is to the previous coordinates minus z deduct. So this is what we call alpha. And whenever I write something like this, I mean manifold. And if I just write a form, of course, the distribution is the current part. So what is V? V is the span of two vectors, of course. So this is going to be in dz. Let's call it V1. Of course, this is the kernel. And then you're going to d2, which is z dy plus d w. And if you plug this in, you see that it's 0. So these are two vectors in the kernel. But if you take the bracket between v1 and v2, you see that what you get is precisely d and dy, which is not in the kernel. Yeah, so this is to represent that. And in fact, this vector field in particular, not because it's the bracket of the generating vector fields, but just actually for the one it is, gets a special name. So if you start with a contact complex manifold with a distribution given by a unique one form, or otherwise you can think about locally, but for the definition, you really need to fix a form. Contact, globally defined. So this globally defined, I mean, once more that V is the kernel alpha for a globally defined one form alpha. We say that R is the Rab vector field for the distribution associated to this form. If it's in some sense very orthogonal to this distribution, but then you also ask that if you take the alpha and you contract with R, you get 0. So you want this vector field to be not in the kernel, but in the kernel of the d alpha. And this d alpha, if you again look at the shape of these local forms, this d alpha is nothing but d, zj, wedge, d, z. It would be wj, and then you sum over everything. So if you're a bit familiar with this type of math, you will see that this is basically a symplectic form. So a holomorphic 2-0 form, such that this n power is not degenerate. With the only of all that the dimension is wrong, right? In the symplectic manifold should be even dimensional. This is odd dimensional. What it turns out is that the differential of this form, so this d alpha, is a symplectic form on V itself. Okay. And so what you're asking here is that this vector field R still, in fact, preserves the flow of the vector field actually preserves this contact distribution. Yeah. So you're not gonna kind of move along a leaf in some sense. You're kind of translating each leaf into another. Of course, there are no leaves at all because this is not integrable, but you can think about it that way. So yeah, observation, the flow of R preserves the curve. And this will be very important later because I will be considering automorphisms. And of course, flows are very useful for automorphisms. So that was more or less a brief introduction of what a compact manifold is. So I'll be extremely quick about what hyperbolic means. We talked about compact, even hyperbolic. So again, we have our complex manifold. Complex manifold. We take a point, and we take a direction. We define is immediately Kobayashi hyperbolicity, something which resembles the norms of this vector, and is defined as the imp of 1 over lambda over all holomorphic disks going through P and tangent to P. Some space here. Okay, so the usual Kobayashi pseudometric, this kind of measures how big of a disk you put inside tangent to this direction. The bigger the disk, the smaller is the length of the vector. And once you define something like this in a typical Finsler fashion, you can take a curve and define the length of this curve just as the integral of this quantity. So add all the infinitesimal lengths. And again, once you have then lengths of curves, you can easily define the distance between 2 points, or what in fact right now we have set the distance as the imp over all curves connecting these 2 points. The spaces are here first. And so, of course, there is no need for this to be absolute distance. It can assign 0 to some vectors. For instance, if you have a copy of C going through the point, the length of the vector will be 0. But when this does not happen, we say that M is hyperbolic, normally Kobayashi hyperbolic. Today, just hyperbolic. If the distance. And perhaps the interesting theorem here, I mean, there are many interesting theorems, as you all very well know, that M is hyperbolic if and only if D induces the manifold topology. Induces the manifold topology. Yeah, of course, I have this distance, which in principle is nothing to do, maybe little to do with the topology of M. It turns out that when it is a distance, then it's a distance which respects the topology of M. Okay, so since we used so little time to discuss what is a manifold, now I can take, and I took some time to describe what is a compact manifold, what is a hyperbolic manifold. I can take some time to discuss what is a compact hyperbolic manifold together. That's one word. And I want to take time, but not space, so I'm just going to add some things here. So what is one compact hyperbolic manifold? So we have a complex manifold with the contact distribution on it. We take a point in the manifold and we take a vector which is not now in the manifold, but really part of this distribution. And now we define a new infinitesimal pseudo distance, again, as the info of this, but now we don't want to take any holomorphic disk tangent to this V, but we want to take only those which are legendary, meaning tangent to V. So legend, and let me define what it means. That F from, well, let's just stick to the disk because I will not use it in other cases. The definition can be made a bit more general. Is the legend if the derivative at every point, and this shaky notation, but you can understand. So we only restrict ourselves to consider this vectors. So we assign a length, this Kobayashi pseudo distance pseudo metric, to vectors in V. And then we kind of want to do the same thing, but now again, our curves. Since I only know the length of vectors in V, I also need my curves to be in V. So I'm only allowed to use curves tangent to V. And then I define the length of such a curve, just the same interval, and this is well defined because this derivative is in V, and this is well defined. And now for 2 points in the manifold, I define their contact distance between them as the inf over all curves satisfying this property. Yeah.
Is it clear that they should go to this?
Yes. So this is a theorem by Chow. It says that every time you have a contact distribution that is more general than that, it's connected manifold, of course, you can know between 2 points, you can always find a curve tangent, piecewise continuous curve, which is what the branchable curve, which is tangent to distribution at every point, and it can connect any 2 points. So yes, this thing is not less than 20, unless the manifold is disconnected. And yeah, this was one of the next observations, so we can skip it, right? And then we say that M is contact hyperbolic. Again, we'll skip Kobayashi today because that's the only hyperbolicity I care about. If the V is a distance. And so of course you see now that if you stay tangent, like if you want to move tangentially to the distribution, this is more or less a Kobayashi distance. But if you want to move orthogonally to the distribution, it's gonna take longer, right? It's more effort because you can't just go straight in that direction. And I do this because I think of this direction as up. I think of this y direction, which is direction not in the distribution, as up. So it's hard to go up. You have to kind of go around, and this takes longer. It's more distant. So perhaps it's not so clear that this should induce the same topology. But we worked this out together with Filippo Bracci and then McKay. That M is contact hyperbolic if and only if dV induces the manifold topology. So there is something similar in the real case, which I didn't mention, but just think that all the variables are real and all the manifold is real, all dimensional real, which is more precise than this, because it really tells you that, yeah, if you want to move tangentially to V, your distance is the same. But if you want to move orthogonally to V, then the distance gets squared pretty much, or square root. So if for small values, like nearby points, if you want to move orthogonally, it takes precisely square root longer. So in some sense, it's the same topology, but it's a different metric than the Euclidean metric you're given, say, the Riemannian metric.
Such estimates are already due to Gromov. He has a book of the stuff.
For the
much more general than just contact.
Yeah, for the real case.
Yeah, but it applies too, because his case covers the complex too.
But you need to start with a Riemann metric, no?
Yeah, well, it's,
Well, here you kind of just start with the complex structure. Then you would need to assign a property. But yeah, we can talk about it later. But the thing is that here we only use the complex structure and the content distribution, while
actually, he has estimates showing that the distance will, of course, I mean, it's intuitively clear that it will depend on the number of commutators you need in order to reach the whole tangent space.
yes, ball box here.
Right.
Yeah, and we
Ball box.
didn't find a complex ball box here, let's say. So if you know that it exists.
Although in this case, locally, it's very simple to see this locally.
Yeah. In fact, that's how we prove everything locally, and then everything is locally. You have one model and everything. Maybe another comment about this is that there's another way to define the Kobayashi metric in general, which is instead of using curves and lengths of curves, you do it with chains of disks. If you're familiar, good. If you're not, forget it. And of course, you could try to do the same thing here. So you want to connect 2 points with chains of Legendrian disks. And this does define a metric, let's say, of pseudometric, and then you can say, okay, now it's hyperbolic, it's defined a pseudometric. But in the Kobayashi case, one can prove, Kobayashi proved, that these 2 metrics are the same. You can take lengths, you can take chains of disks, and this is exactly the same thing. We did not match.
Actually, this was Kobayashi's definition, right? The other one is Royden.
This is Kobayashi.
Well,
This is Royden.
the one infinitesimal metric and integration. This is Royden.
Okay.
Kobayashi did chains,
Okay.
but it's the same. Is in the contact case is the same too? Same.
We don't know.
You don't know.
We tried.
Because it's a problem how to make a chain of disks which are Legendrian and actually match points correctly.
No, this is okay.
This is okay. Then it should be the same, no?
Yeah, that's what we believed. And I remember we worked on it, but I don't remember the details. It was more.
There was a similar problem recently treated for the minimal metric by Gaussier and Super. And I think that in their case, they managed to show that it's the same.
This was also some years ago.
But
I remember,
I
don't remember why precisely didn't.
I don't know why people like these chains, because personally I find this definition much more natural.
And this also is much, especially when you will do contact, I think, this resembles a lot more what people do in sub-Riemannian geometry, which is basically the real version of this. So you can borrow more easily, perhaps. Okay. So why did we start? So yeah, maybe I should have mentioned at the beginning, what I'm talking about today is joint work with Bracci and McKay. And so we actually came at this in 2 different ways. I wanted to, I mean, of course, I learned about this hyperbolic manifolds from France. And I was interested in studying maybe their group of holomorphic or contactomorphism, which we'll define in a second. And I met Filippo at a conference. I told him, oh, this is what I'm working about. It's like, oh, I started working on this 8 years ago with someone, and now then everything is done. But in fact, they were very much interested in more about this metric stuff and reproduce this Kobayashi metric in this contact case, then discussing automorphism. So then we put things together, and we came up with this 40 pages paper, preprint. But yeah, I was more interested in automorphism, so this is more what I'm going to talk about today. And if you care about the metric part, you should ask it.
And this metric has similar properties like we've seen.
Yes, absolutely. But not for every map, for maps that preserve the content. In particular, automorphisms will be assumptions, which is very nice. So let me just quickly define what is an automorphism for us. This is, so we have our favorite contact hyperbolic. And the group of automorphisms, contactomorphisms we'll call them, is the group of those automorphisms of M, is intended as biolomorphic maps, such that the pullback would be is V itself. No, so you can preserve the distribution. If you want to see it in local coordinates, which is very helpful, if V is the kernel of alpha, this is the set of automorphisms that don't really need to preserve alpha. They only need to preserve it up to a non-zero holomorphic function. Yeah, you have to preserve the kernel of alpha and only the kernel of alpha. So you're allowed to multiply with whatever. And in fact, any two contact forms for the same distribution only differ by such lambda. And even if you don't take this lambda but a different lambda, of course, the group stays the same. And yeah, as Luca was mentioning, the fact is that the distance between P and Q is the same as the distance between f of Q and f of P. Or f. Of course, there is a more general theory of maps between contact manifolds. So you want the contact distribution of the source to be sent in the contact distribution of the target. But since we're just doing, and then there is a decreasing theorem. But since we're just doing automorphism, we really say that these are isometries. And once you see this, you really, and if you know a bit about Kobayashi hyperbolicity, you will know that there is a theorem by Isaac, or maybe a better say a series of theorems, of which I would state only a part. Then if you take a hyperbolic manifold of dimension n, so this is just not contact, just hyperbolic, then the group of automorphism is a real group of dimension at most n squared plus 2n. And if the dimension is n squared plus 2n, then the manifold is long. So I'd say this is a very strong, interesting theorem. It uses a lot of representation theory, and it's in fact, as mentioned, much deeper than this. Meaning, okay, you have this bound, but then somebody maybe correct me if I'm wrong. I'm on top of my head. I think then there is nothing until n squared plus 2. So there is no hyperbolic manifold of dimension n with a group of automorphism with dimension between n squared plus 2 and n squared plus 2n, extremely excluded. Then n squared plus 2n, you can describe explicitly the two examples that arise, I think. And then for n squared plus 1, you start to have more examples, but I think there is I don't remember if it's complete or almost complete description of this as well, or maybe if you add some hypothesis, then it's complete. And then you keep going even. Not of course, once you ask that there is no symmetries, then of course you can have whatever, but if you ask for many symmetries, meaning a big dimension of the group, then you can actually characterize. And so what I saw this, I was like, okay, there must be something similar, right? There must be something underneath, because the first thing they use is a theorem by Buckner that tells you that if you have a group of isometries, then this is a real group of finite dimension. So these are these are isometries, so it's a finite group of it's a really group of finite dimension. Perfect. Okay, great. Can I say something about? Can I give an estimate here? Can I give a top level estimate? Can I characterize what happens at the top level and this kind of stuff? So to do that, we want to lean on something which is symplectic manifolds.
Is there a theorem saying that a generic manifold of this kind has no automorphisms?
Not that I know.
Will be the case, no?
I mean, yeah, if you take most yeah, like if you can think of anything, this would be just identity, right? But then generic, you need to put some kind of topology in the space of all manifolds. Yeah, sure. But there is
I
no.
mean, for some classes of manifolds, it's true, like for strongly pseudo-convection.
Yeah, exactly.
No,
Yeah, exactly.
But
Yeah, there is some kind of almost stratification.
Yeah, but what about for that's an interesting question, maybe for compact projective manifolds, you know?
For getting the
Because
hybrid.
there are lots of these conjectures, what is true generically.
Yeah, I don't know if there is such a thing. And I didn't think about it. So we wanna, so as I mentioned, this contact distribution by itself, it's kind of a symplectic manifold. It's not a manifold, but it has some symplecticity into it. So let's say that we start with a contact manifold. The hyperbolic, I mean hyperbolic, yeah. So with the form globally defined by one form, and let's say that R is the Rab vector field for alpha. We say that the triple MBR is a Rab manifold. This is no something like it's the name we came up with. If R is C complete, and yeah, and it has B. Let me mention why we looked at this. So this is a bit of a restriction. So you want to start with any contact manifold, and ideally say something about any generic contact manifold. But we do want to study contact hyperbolic manifolds. And of course, if you start with a manifold which is already hyperbolic in itself, you put whatever contact distribution you want on it, this is going to be contact hyperbolic. So in some sense, it's not really worth studying contact hyperbolic manifolds where the manifold itself is already hyperbolic. So this is a way to say that the manifold M is not hyperbolic. Because if you have a vector field, which is C complete, and not zero, of course, then you have copies of C inside. So in some sense, the transverse direction to V contains many copies of C, so it's not hyperbolic. So we're kind of putting a lot of zeros of this symmetric transversally to the function. And the fact that we ask freely, well, basically, it's some kind of non-periodicity in some sense, right? So we don't allow this orbit, this C complete orbit, these copies of C to become copies of C star, for instance.
But did we say that there is parallel?
Yeah. This is not. The red vector field is not parallel to.
No?
No, it's very transversal. It's very transversal.
Yes, yes, yes. So I will this
I did not contact hyperbolicity because you're not hyperbolicity.
Okay, okay.
Because I don't want to study hyperbolic manifolds with context. Any expert. So yeah, this really it's more of a kind of technical assumption. We don't want to deal with the possibility of this C wrapping around. This is a bit of a restriction for sure, but it is a stepping stone. It's the beginning. And this is also what was done in the real case. So in the real case, they also consider these Rab vector fields, and they study a lot the orbits of this Rab vector field. Usually doing a compact manifold, so it's always complete. And it's very interesting to study these orbits because some of them are going to be closed and periodic, so you're going to have copies of S1s, while the other ones are going to accumulate on this periodic orbits. And so then it's interesting to study how this happens. There is a whole cohomology called floor cohomology behind it. And a lot of things I don't know. But this is an initial restriction which makes sense.
So in the standard case, it is the y direction, which is The C3,
yeah.
Y direction.
Yeah. By minus Z W.
The other fluor, what is they call
Z and W.
Lagrange.
The directions.
The other fluor.
Lagrange.
Lagrange. Yes.
Okay, and our theorem about this manifold, our initial theorem, is that if you have M per alpha R Rev manifold and contact hyperbolic, so now I have to ask contact hyperbolic of dimension 2n plus 1, then R acts properly, so not just freely, but properly. The automorphism group is a really group. With dimension between 2 and 2n squared plus 5 and plus 4. And this is a terrible bound. Okay? But it is a bound. So let's start with the 2. So the 2 is just really this action of the C complete vector field. This is action of our 2, let's say. So I have 2 dimensions and I always have them at these translations. And this, you basically look at the proof of this result. There is some a representation theory in here where this n squared comes from actually from the dimension of the orthogonal group. And while the 2n is the real dimension of the manifold, and here you kind of copy paste the argument, except that now your group is not the orthogonal group, but is the symplectic group, because there is some symplectic there. And you just copy it, and then you realize that this is a terrible bound. Okay? And you should be able to lower it.
Do you have a conjecture for a better bound?
No. But we have a sharp bound in dimension 3. But that's it. And it's not this. So dimension 3 is n equal 1, and this gives 9, 11. Well, the optimal dimension is 7. And there's only one example in 7. So the idea is that every time you have such a Rev manifold, again, M alpha R Rev contact hyperbolic, there should be, or maybe you hope that there is, some symplectic manifold. So symplectic just means that omega 2 form, the omega is 0, and omega is nowhere 0. It's a very well studied thing. And you hope that there is a map phi from M to S, and you call it a contact is a contact symplectic lift. If it is a C principal bundle, if it is a C principal bundle, with C action given by the Rev, I will explain everything. And the alpha, which is our ideal symplectic form, is just the pullback with a minus sign for technical reasons of the pullback or downstairs. Okay, so let's look at this for a second. So my vector field here has this action of R. What I'm asking is that this action of R is actually the action of a C principal bond. And this phrase here, R acts properly, is fundamental to proving that this kind of stuff exists. So the idea is that you can start with any symplectic manifold, and you want to somehow lift it to some revenue. Okay, so you should think of this as sure as a way to describe M, but more so I start with a symplectic manifold, maybe I add something to omega, and then I want to produce an M, which is a contact manifold. Perhaps I want to produce all the M's, which admit S as a base, this kind of stuff. And so, for instance, an observation, if you fix S and omega, the possible, so fix as omega, the possible M's are classified. So these are just the total space of a C principal bundle over S. So just by H1 S. Oh, but nothing special. And we can also prove, in fact, here I don't need the hyperbolics. Here, that MV is contact hyperbolic. If and only if S is hyperbolic, that's the standard. So maybe to give an example of this, just again, so we have a picture in mind, which in fact will be the only local picture. So that's why it's important to give it an example. You take S omega to be the bidisk with the so-called standard symplectic form, and then you want to lift it. Well, your M alpha can be only one thing. So topologically, like as a complex manifold, we have only one choice, of course, and this is the trivial C principal bundle. And then you might wonder how many forms I have here, and we can prove that there is only one form, which is the standard form. Sorry, I used W somewhere. No. Yeah, and this is, so locally, every lift looks like this. So this is the local picture.
Would you should take more general domains instead of the bidisk?
Absolutely. You mean for the standard picture or in general? I mean, yeah, sure, absolutely. Yeah, you absolutely want to do this. This is just to show, this is the most basic sample that comes to mind. And the local picture always looks like this.
I mean, can you take any hyperbolic in C2?
Sure.
With the standard symplectic form?
And then lift it? Yeah. Yes, there is examples. Yes. Well, can you take any? You said ask any. Can you take any? There is some questions of Koma.
Yeah, sure.
No, if you take the standard form, if you take the standard symplectic, then you can always lift it. So the condition that you need actually to lift it is that you have a symplectic form, which you don't need it to be exact, which is what almost looks like. I mean, you don't need it to be holomorphic exact. It's enough that it's smoothly exact.
Before you mentioned so it's non-bidisk.
Yeah.
And 7 sort of unique.
Yes, and it's not this.
So
it's not this. If it makes sense.
No, I'm just asking, what is this? You know, we have what this manifold.
Yes. Not only the manifold, but you really need to specify the contact form as well.
Yes.
So different contact forms in principle might be. It's not this one. This one is dimension
3.
No, 4 or 6, I think. I have it something here.
Oh, yeah.
Both is dimension 4. 4. This is dimension 4. Because you always have 2 dimensions in this interaction, and the rest they need to be the symplectomorphism of bidisk, and this is only U1 times U1. So yeah, to answer maybe that question better, can you do this with any domain pretty much? So if you take symplectic, and you take omega smoothly exact, so it is a holomorphic form, but you can ask that it has a maybe not holomorphic primitive, then there exists a contact symplectic lift. This. And the possible amps, let's say, M alpha, actually, so the pairs, M alpha contact symplectic lifts up to equivalence. It's in bijection, not with H1SO, because this is just all the possible M's. If you take the form into account, this turns out to be in bijection with H1SC. So now it's, I think, the perfect time for this other example, where S is D times D star. And this is a nice, and the omega we take the sound for. This is a nice example because H1SO is 0, because it is a Stein manifold, but H1SC is non-zero. So there is only one possible M, namely the trivial one, but there are C many one forms on it, which are non-equivalent. So alpha C is dy, and it's pretty easy to imagine what they should be, but maybe it's not so obvious why these are really all different. Well, I mean, it's not that high. So the standard form is dy minus zdw, and it happens for c equals 0. But then you can add a twist by adding this kind of singularity, 1 over w in dw, which is perfectly allowed. And yeah, different C's produce different contact manifolds. Yeah. And this you can repeat for everything. So one thing I think I asked you in Levico, which was not Levico, do we have a hands-on example of a manifold with a symplectic form, which is holomorphic, but not holomorphic exact, but smoothly exact? So can you produce something which is not this? And of course, these exist. But to produce something by hand, at some point we just gave up. And I still gave up. Huh? Okay. So back to automorphisms. Space. But yeah, maybe the main point there is that there is a difference between classifying the possible amps, and this is just classifying C principal bundles, but then on top of that, you can classify the different forms on. And that's the bijection. And the thing here, like if you look at the proof, basically the idea is that when you have something which is smoothly exact, but not holomorphic exact, so the condition was the alpha is minus pi star omega. So, you know, if this is holomorphically exact, then you're going to just find a primitive, and that's it. But if it's not, I mean, omega, if it's not holomorphic but smoothly exact, you hide the smooth in the twisting of the bundle, pretty much. So you're not going to get this trivial space here, you're going to get something more complicated. This is going to have some transition functions, and you hide the transition functions, like you choose this transition function in such a way that then on the total space, this pullback becomes holomorphic exact. So it also means that in this case, the manifold is fixed and you only change the form. But when you really have something here which is not fixed, you really have to change the manifold and the form at the same time if you want to look at something like a continuous family. But okay, I am digressing. Automorphisms. So there is a relationship between the automorphisms the contactomorphism of MB, and the symplectomorphisms of S. So we define automorphism of C omega S as the automorphism of S, which are not symplectomorphism, but you call it conformal symplectomorphisms. So symplectomorphism up to a conformal form. And there is a map. So every time you have a contact symplectic lift, there exists a map phi out Bm out C omega S Lie group morphism with fibers given by the action of iron. Yeah, so the red vector field acts transversally in a way. So whatever modifies that doesn't really modify this V will not be seen upstairs. So these are what the fibers are like. In general, the map is not surjective, but it's surjective in most examples. And the theorem finally that is really this classification is if you start with M alpha R contact hyperbolic reb, contact hyperbolic and reb of dimension 3, so I'm just dimension 3. Then the dimension, as we knew, the dimension is less or equal than 2 and at most 7. And this 7, as you say, is better than 11, right? Which is what we had before. And sure, it's strictly better. It's strictly better. And if the dimension is exactly 7, then M is the ball and C with contact structure. Because of course, yeah, this is kind of easy to say. I mean, the only lift of the ball is C itself. With lift, with contact structure given by the lift of the ball with omega, not the standard form, but this one. What is this? If you look at it like this, it's a group with a symplectic form. It's a manifold with a symplectic form is a perfectly defined symplectic. So maybe to understand it better, the question is, what are the automorphisms of this, the symplectomorphisms of this, or perhaps the conformal symplectomorphisms? Because this is the interesting part. This is the 5-dimensional group. Dimensional group of automorphisms of B2, fixing the point 1, 0 bound. So there's this deja-vu theorem that all the people in dynamics sort of know very well, that you can classify the automorphisms of the ball based on how they behave with their fixed points. So there are automorphisms of the ball which have a fixed point inside. There are automorphisms of the ball which have 2 fixed points on the boundary. And there are automorphisms of the ball which have only 1 fixed point on the boundary. And it turns out that, and each of them, of course, you can think that there is a group of stabilizers. So the stabilizer of 1 point inside has dimension 4. The stabilizer of 2 points in the boundary has dimension 3. and the stabilizer of just one point has dimension 5, and this is the only 5-dimensional subgroup of the group of automorphisms of the ball. Not just this, of the full automorphic group, but it's the only 5-dimensional group. So if you really want to get to 7, and we took a long time to get to 7, because finding example with 6 is easy. So here the fibers have dimension 2. So if you want this to be 7 and this to be 5, and so you have to somehow find a subgroup of the automorphic group of the ball of dimension 5. And this was in some old paper by Filippo and Benjamin on completely different stuff, like it was on dynamics. And this was in an appendix together with the IMs, because it was not even an important part there. And they remember that, yeah, we did this 15 years ago. So I think to me this is very striking, fascinating, also because it has this random intersection with dynamics, which is of course something that always happens if you work with Filippo.
So in this case, are you saying that these automorphisms, which this 5-dimensional group, these are the what you call parabolic, right?
Yeah, exactly.
These lift to automorphisms
of the contact.
Yeah. And then on top of it, you have the flow
of the ramp.
and that's it.
That's it. Precisely.
How is in general this map C defined? Is it something obvious or?
Yes, yes. Because basically, so you look it on local patches, and locally everything looks like this, no?
Yeah.
So you already have some Z, something that happens to Z and W. You already have it, and you basically just look at the ZW, like the map. Yeah, the map would still be ZWY goes to ZW, basically, no? So you basically only look at what happens in the ZW, and that's it. And it turns out that you get a conformal factor.
No, but you have to have some lifting. I mean, if you find an automorphism of
for the other way around, the lifting.
If you want to define an automorphism of S,
yeah,
then you first need to put it somehow into M, no? And you put it as a slice, or
no.
No?
No, I mean this is the local picture, right? But then you have to glue this together.
You have to.
So then there is still something to do. But locally, it's this. So you take a local expression for this for an automorphism here, and if you put everything in the contact symplectic lift coordinates, this is what it looks like.
Okay,
but it needs to be in those coordinates.
So locally, you take a trivial lift of S into M, then you apply automorphism,
you can think of
it project back.
You can think of it like that. Yeah.
Something like that.
Yeah.
Yeah. Okay, that's what I wanted to know.
Yeah. Yeah, trivial in the sense you take y equals 0. Huh?
Mm-hmm.
Yeah, sure. You can take that way.
And then you have to show that it's well defined.
That it's somehow glues, yeah, exactly. That when you, because the point is that when you change patch, let's say when you change realization, the Z and W actually stay the same up to a conformal factor.
Up to a constant, yeah.
Yeah, and the Y gets something like the new Y is going to be something like Y plus F of ZW and the old Y. So like principal bundle, right? And somehow you have to show that everything goes. And when it doesn't, if instead you start with a ZW and you want to lift it, so you want to go the other way around, you will see that not all of this lift, because sometimes it doesn't go.
Yeah.
But if you start with something that you already know it glues, because it's an automorphism, then it works.
So that example is super simple in that sense.
Yeah, because when you have a very large group, things are going to be the same. But you need all those symmetries. Right? But the interesting thing that comes out is that you don't have the standard form, but something different. And maybe just to complete, we do have other examples. So we have B2 times C with the standard form, dy minus ADW is a dimension 6. Then you have D2 times C, and you lift 2 over 1 minus z squared, dz wedge w. This gives you dimension 5. Then you have the standard d2 times c with dy minus z dw. This is dimension 4. And then you have d2 times c, and you lift something a bit less homogeneous, like 1 plus z dz wedge dw, is dimension 3. And then for dimension 2, as you were saying, you can take any Kobayashi hyperbolic manifold with no automorphisms, and you just put in dimension 2. So this D is any Kobayashi hyperbolic manifold of dimension 2 with no automorphisms. And okay, thank you for your attention. That's pretty much what I'm going to say.
Okay, there are questions. Let's thank Filippo.
Oh, great. Yeah.
We listened so much about Filippo and your talk.
That counts as an upgrade.
Yeah. It's